ramp pressure shifting might affect them, ionization might affect them, even though these are the current Emaxes, it's possible that Emaxes could be bigger. But basically, this is the situation as we see it. Emaxes are fairly small. So is it ever going to be possible to really know without assuming the theory prior? So everything about 500 line of sight velocity stars, the typical force, this is just an example experiment. If you're trying to measure beta, you can't do it. There's a huge degeneracy, and this is Vmax just plotted in this plane. Then let's say in the future, now we have 1,000 line of sight velocity stars and 500 proper motions from SIM. This is what happens to the gamma. It shrinks considerably, and you basically nail Vmax. Similarly, with this kind of data, we think that you'll be able to, even though there's a huge degeneracy, I think right now, between whether there's a cup or a core in these little guys, data like this, I think, could possibly constrain it. Now you're talking about proper motions that can really help you. So principally, I think it's going to be very interesting, and then you're doing, if you think about the nature of dark matter, you're doing fundamental physics with SIM. So let me move now from Dwarf scale to galaxy scale, and talk about probes of galaxy halos. I'm just going to mention a few things. I think a lot of these will come up again, but I thought since I was sort of early in the program, I should mention some things. So satellites at random velocities in external galaxies. You're looking at external galaxies, trying to get a feel for what the dark matter structure is, what the substructure is. So there's this work by Bonnet et al. Used Sloan to measure the kinematics of satellites around galaxies, and they find, I think, a very interesting result. That the outer halos do seem to fall off basically as expected within a second. It has to be the case. It does not seem like the thermal at least have large radius. Satellite orientations, this question of whether satellites lie along the poles. There are experts in the audience on this, but interested in what they didn't have to say about it, so kind of have to say that much. But the way I read it is, if you specifically are focusing on red galaxies, you really do see satellites oriented along the major axes of galaxies. And that might be expected if they formed in a major merger, sort of along the filament, the direction that the halos are part of pointing. But the Bonnet et al. Result, they specifically were trying to focus on galaxies that they knew were disks, and they found no conclusive evidence of any specific orientation. Now, another thing you can do is look at stellar velocity dispersions around galaxies, and you fall into the same kind of degeneracy that we're talking about with the dwarfs, and you really can't use it to probe a halo, but it's certainly consistent with what we know. Now, you think about satellites and random velocities around the Milky Way. So satellite orientation, you have this issue of the polar effect where the satellites tend to sit in the poles, which may be an issue, and I don't think we know what to do with that exactly right now. Stellar streams of Sagittarius, which Julio alluded to, it looks like the halo is quite round. This maybe has something to do with baryonic effects. And stellar halo velocities, there's a big degeneracy. And again, it's quite hard to probe for the same reasons. And there's a very nice paper by Bonnet et al. Who basically laid this out. It's very nice. And I think in the future, as we get more and more stars, and more precise velocities, not just radio velocities, but time sequence velocities for some of these things, it's going to open up a brand new window for really precise probes of our halo. So let me just throw this up here right now. Another thing we have to worry about on galaxy scales is the mass-to-light ratio issue, that is, there's baryons there. These are just estimates of the mass-to-light ratio of central galaxies as a function of dark matter halo virial mass. This is roughly one of the baryon factors, so we get a very efficient galaxy formation here. But in some sense, this is bad because we've got baryons here. So when we're focusing on dwarf galaxies, that's not what we're talking about here. That's kind of nice. We're talking about dark matter structure. Here in clusters, again, we may be able to use our dissipation simulation. But in this region, things get a little bit messy. So on galaxy scale, baryons affect halo shapes, as Julia mentioned. So you've got halos that are elongated, and it's gas cooled in some of these galaxies that make them more spherical. This might help explain what's going on with the Milky Way in this extreme. Currently, there's really no strong evidence that this kind of effect actually operates in clusters. So, for example, borax et al. Study a bunch of X-ray cluster isotopes down. They're basically consistent with the shape of the cluster-type halos in simulation. Then I'll also affect the density structure of halos. Again, this is an issue that people are worried about. So as Mendon et al. Showed, dark matter halos should adiabatically contract even in cosmological simulation. But there's evidence against this if you take it plain seriously from the polyhedral relation of late-type galaxies. X-ray studies of massive early-type galaxies, Humphrey et al. Basically find that you can't really do anything reasonable with the stellar mass-to-light ratio. You try to include adiabatic contraction and also galaxy clusters. So there's some evidence, in some sense, you can think of it as evidence against it, at least there's no evidence that actually happens in the real universe. Although there is some evidence that it may happen sometimes, especially close to home. This was led by Mark Seeger, who's also a postdoc at Irvine, who's constructed a new mass model for M31 with a new baryonic mass estimate. And basically the deal is that the rotation of M31 falls off, peaks and falls off, is understood quite well, as well as the mass distribution of M31. You can't explain this without significant adiabatic contraction. So this is the Blumenthal et al. Model, which is about the most that anyone ever talked about. And this is basically what we need to get. You turn off adiabatic contraction, it takes me possible to get this full. So I think this is evidence that it happens, at least if you believe CDM or believe something like this. This is evidence that it does happen, at least sometimes. So that way you get pretty reasonable masses and concentrations. So I'm going to move on here a little bit and basically just say that another idea that maybe the adiabatic contraction does operate, but just the typical concentration for galaxies are lowest, we might have thought, for some reason or another. And this might not be crazy if you think of the bias in the type of galaxies, the type of halos that specific types of galaxies fit in. We know that low concentration halos tend to form late, and high concentration halos tend to form early. That's the trend explains the trend with mass. But also almost in a one-to-one way, if you take this plot and slice it to fixed mass, the trend with formation plot is very tight. So it's almost like a one-to-one map. This relation is even stronger than the relation with mass. So you might see there's a very good reason to believe that there should be some kind of bias. If you're looking at one type of galaxy versus another, you're looking at a bias part of the concentration distribution. So you might think that maybe late-type galaxies live down here, and early-type galaxies live up here. And high concentration systems even cluster more strongly than low concentration galaxy halos. And this is the work I select this. So this again might point you in that direction. Now, let's think about the concentrations of larger mass systems. Now moving to group and cluster size halos. And you can do a similar thing. Again, you show that the same trend happens, but if you look at, for example, the number of satellites, the number of subhalos these halos have as a function of formation time of the object, again, things that form early tend to have less substructure, or fewer satellites than things that form late. So you have the same trend with concentration in the number of satellites. So this might suggest, for example, that low concentration systems have many satellites, and either unrelaxed groups and clusters. Systems that are relaxed, or things like fossil groups, might populate high concentration pairs. You might suspect that what's going on is something like this. Here you've got fossil groups and relaxed clusters, you've got unrelaxed and merging clusters, late-type galaxies, and early-type galaxies. If this was the case, I'm just presenting it as a possibility. you need to sort it out, because if you're normalizing your model against this medium concentration relation, if you're looking at a specific type of galaxy, you're in trouble. I'll just close with this figure. This is a figure from David Gluat et al., the X-ray group at Irvine. The compilation of 39 relaxed systems, it's XMM and Chandra data, the best data they could get. It includes early type galaxies, groups and core clusters, and massive clusters. And what's shown here, this should be out next week on AstroPH, is the concentration mass relationship in the X-ray. The one thing that you can see right away is that there is a trend with mass. As far as I know, it's the first time it's ever been shown, observationally, that there is a trend with mass. Second of all, I don't know if you want to take this seriously or not, but here's sort of the LCDM sigma 0.9 line. These massive, very early type systems are about 1 sigma high. These are very relaxed sort of proper group type systems. They're about half a sigma high in the concentration plane. I think that's interesting. Possibly, going out the picture. So here's my conclusion. For density profiles, closest and rotation curves, late types need lower concentration or no adiabatic contraction. The X-rays, natural elliptical relaxed with the clusters clearly have a CMM relationship and also need slightly higher concentration than typical. Substructured word counts, we just don't know. We need better data. There's huge degeneracy in that issue when you're looking at velocity movement profiles, in my opinion. Satellite orientation should orient with a major axis of payload. Elliptical, I think the evidence is good. I think we need more data on this. Shape, basically, I think there's general consistency, especially because the calculus is very opposite. That's sort of on the over.
Okay, Daniel. Thanks for listening. Just something was prompted. Let me just say a few words about satellite orientations and spirals. In a study led by Jeremy Balin that should be submitted any day now, we've been sort of reworking through the entire literature of studies. The problem has been that since our initial sort of homework effect detection back in the 90s, other studies have come back and said the satellites are oriented the other way. So we've been trying to understand what the source of the discrepancy is. We've been looking at numerical simulations on how you pick satellites out and how interlopers come into play and so forth. And we found basically that the problem is in how you define an isolated galaxy. And if you define an isolated galaxy differently, you get very different results. So we've gone to the simulations and looked how to really truly identify things that are isolated. And we've applied that to the flow data, which is what previous studies have used and gotten anti-Holmberg effects. And we actually recovered the Holmberg effect again. So it does look like satellites around isolated disk galaxies do lie differentially around the poles. And we can reproduce all previous results if we take their criteria for isolated galaxies. So I think the situation is clearing up now.
I like the sort of idea that you sketched about how concentration can vary with population and so forth. And it's certainly very tempting to believe that, for example, the list of reflected galaxies or late time formation, lower concentrations, matches, both their stellar populations and their spatial distribution. But the problem, I think, one has to be careful with is for outstar things, where it's quite possible to attribute a lot of the mass to baryons to small radii, in which case it is for even lower concentrations for that sort of thing. And so I think, again, baryons are raising their ugly head, and we have to sort out what those are really doing before we can, I guess what I'm saying, if I'm worried, this one makes sense, but it's easily get out of the way. I mean, I was kind of happy that at least the concentration was reasonable for M31 when we included their gas attraction. Like, they had only one system instead of gigantic bulge,
Question?
I'm pretty sure that typically where you claim on a just short concentration index. Yeah. So you typically would know. I mean, so since this is they don't almost like sigma 8 concentration does. So if you bump sigma 8 to 1, it would really bring it up. No, but that's in the opposite transport with WMAP getting right. Right. Oh, WMAP is way low. WMAP is, you would have to be, if you took the WMAP seriously with the tilt and everything, these are sort of 90%, 95%. Sorry. If you take it seriously and think this is a representative population, I'm not sure it should be. It's ruled out 99% of them. The really high concentrations for the WMAP. Yeah, because they're picked to be. Yeah, exactly. They're picked to be the things. These should lie high. I think if these things were low, we'd be in big trouble. But I think it's encouraging that at least we've got something that have too much.
Okay, thank you, James. We go to the next speaker.
Hello. I'm going to be talking about a paper we published about a month ago after the division of letters. Talking about the emerging galaxy cluster and some observations seen in regrowing from X-rays that we made. We're claiming proves that regardless of how gravity behaves on scale, that we have to have dark matter as the most massive component. So here are the collaborators on the project, the ones involved who are here at this meeting. So the final data novel in 1933, when Ridley first pointed out that the recently measured velocity dispersion of the comet cluster had a real mass that was a couple hundred times larger than what we got if you just took the limited matter of the stars and used the gravity and the data from it. He concluded that either the gravity is non-Newtonian or that the bulk of the mass of the cluster would have some limited matter on the department scale. The subsequent to this, of course, discovered that you have the X-ray cloud-line clusters that we call it, actually make up most of the baryons, about 85 to 90% of the total mass. This reduces the gravity up to somewhere between 6 and 10 times less mass than what we need for Newtonian gravity. And that this assumption has been made usually that we have a lot of dark matter. But the primary reason for this has mostly been due to the fact that we haven't really had a way of calling non-Newtonian gravity theory, which most of them was ad hoc models extending very specific observations. It's very difficult to extend these out to observations of other phenomena. Over the past couple of years, though, people have been coming up with models which could be derived from general relativity, and therefore you can extend them to the gravitational ones and CMB observations and the like. And that's actually sort of been a small explosion in the number of papers coming out. And another primary problem problems is that if you take normal galaxy clusters, these are two fairly massive clusters, they don't contain 1835, which is sort of used archetypical big bell clusters. And what you see is that these are some recent observations we made onto the satellite, and we can easily detect these. However, all the galaxies and all the gas is all located in this area along the dark matter. So it's relatively easy to prove that there's way too much gravity here. So you can't really distinguish between whether the gravity is dark matter or whether it's extra gravity on these low scales without